Now let's review some of the stuff which we talked about last time, some of the stuff you need to know, and that will also help us move forward. So remember, we talked about syntax and semantics for propositional logic. We are with propositional logic. Chapter 7 is still propositional logic. What exactly is syntax? That's the grammar of the language. This is all those structural rules which we use in language. What exactly is semantics? Well, that's the meaning, which of course in English language is very multiple, right? The words in English language have a variety of meanings. But for our purpose, there are only two meanings for our propositions, which are what? True or false. That's it. So it is much simpler than English, and for this reason it is easier to work with it than with English language. So syntax, again, remember, in propositional would be those letters. P, Q, R, which are capital letters, and they stand for specific propositions. Now, when we talk about language kind of from outside, we're using Greek letters. The book uses lowercase English letters, just I guess not to confuse students too much, but you guys should be aware that this is more proper way to do it, and it shows you immediately that that is not part of our language L1. It is meta language. We are talking about what is happening within our language and using this phi and psi to describe that. And remember that we can also have the operators, which is tilde. Then Hurley-Watson uses a dot, but you can also have this kind of upside down wedge for and. You can also have a wedge, which is the same for both of them, for or, this or that. You can have an arrow or horseshoe, as Hurley-Watson does, for if this, then that. And you can have two-way arrow or triple bar, which is again the same thing, for if and only if. This, if and only if that. Okay. Then remember we talked about the structure. Structure is just specific truth and falsity values which are given to you. If they are given to you, it makes your job much easier, and specific assignment of truth and falsity would be a structure. So you can have a structure, for example, where P would be false, Q false, R false, P1 false, and so on. We can give again it to describe this structure some sort of a Greek letter, but typically that would be a capital Greek letter like alpha or beta, capital. Now, truth tables can be created for all of our operators, showing what true values any two propositions will have with these specific operators. The easiest one, remember, is negation, because here you only have two possibilities. If your phi is true, your not phi is false. And if your phi is false, not phi is true. That's it. There's really nothing else that can be happening here. This is kind of a more proper way to say it in words, that under alpha, if f is negated and its value is true, that will only be happening if f itself under alpha is false. A couple of other tables which we also went over, and hopefully you remember them now. Conjunction f and psi only has one situation when it is true, and it is when both of them are true. If at least one of them is false, the whole thing is false, and of course if both of them are false, the whole thing is also false. This is what this first line here tells us. On the other hand, if it's disjunction, if we have phi or psi, that actually will be true in three different situations when at least one of them is true, which is what this line tells us. But there is one situation when it's not true, when it's false, and it is when both of them are false. When the conditional statements, the implication, we have only one situation when it is false, from true to false. If you have true on the left of your arrow or horseshoe and F on the right, then you will have the whole thing false. Now on the other hand, in all other possibilities, it is true. And if it is two-way arrow or triple bar, if it is the equivalency relation, then we have two possibilities when it's true, when both of them are true or when both of them are false. So this is a brief review of all these rules. And remember that in terms of validity, again, what we can say is that when we have any group of sentences, which we can just use the Greek 15. But if under gamma, there's absolutely no possibility that this one sentence which follows from them, C, assuming gamma is all true, C would never be false, then that is what we call validity. It means that then P follows from gamma. Now if it doesn't happen, then it doesn't follow from gamma. If there's any possibility that all sentences in gamma are true, but phi somehow under any structure happens to be false, that is not, then phi is not following from gamma. Okay, so 7 talks about natural deduction. Natural deduction, now we are kind of switching from semantics, from truth and falsity, to syntax, to the structures. And that's the important difference here. Structures can be truth-preserving, and if we keep the truth-preserving structure, then we can preserve the validity. Natural deduction is a method for deriving the conclusion of valid arguments expressed in the symbolism of propositional logic. It consists of using a set of rules of inference. We will learn these rules this week, and I think next week, to derive either conclusion directly or a series of intermediate conclusions that links the premises of an argument to the stated conclusion. So our idea, again, is to kind of preserve this type of relation. That whatever our conclusion is, it would always validly follow from our premises based on this structure. So why do we call it natural deduction? The name comes from the fact that it resembles ordinary step-by-step reasoning process people use in daily life. We are kind of reasoning in this way, even though we are not specifically thinking about it. Similar in some respects to the truth table method, but largely used for invalid arguments because, well, as you will see later, the natural deduction is in some ways more useful, but we can't always calculate and make sure the argument is valid using the structure. Structure doesn't guarantee that. It only guarantees that if argument was valid to begin with, it continues to be valid. Requires more insight and creativity. So that's one of the things to differ it from truth tables. Truth tables are more mechanical, right? You are following the rules like a machine. Here you actually need to be a little more creative. You need to look at the argument and think, what can I do with it now? So this is why this is how proofs are written, right? Proofs are not written in some kind of mechanical way. You need to think more creatively. You need to look at what's in front of you, and like if you took Math 251, you probably know what I'm talking about. They do ask you there on exams to write the proof, and basically you have to come up with your own way. You have to invent it, essentially. Well, here it's not going to be super difficult, but the idea is the same. We will learn these 8 rules of implication, rules of inference, and you can apply them, any one of them really, to preserve the validity of an argument and to kind of derive something there based on whatever you're given. Okay, so the first rule is called modus ponens. They do have names, by the way, and you need to know their names. Modus ponens. If you look at the structure itself, so it starts if P, then Q, then P, and the conclusion Q. So remember that this is also like we're not using the Greek letters, but that's the same idea. That is not actually sentences in our language, L1. This is just kind of a meta language describing any argument which has this specific form. Now, if argument did have this form, what would we call it, by the way? Huh?
Valid?
Well, hold on, it's not about valid, but remember the argument forms which we talked about at the beginning of class. Obviously, we are with deductive arguments. So deductive argument forms. We learned 5 of them. 2 of them don't really apply here, like argument based on mathematics and based on definition. We're not dealing with them because they are not really formally bound. Not formally deducted. But there are 3 other ones.
It's categorical, disjunctive, and hyposyllable, something like that.
Yeah, so which one is this? That's the question.
Disjunctive.
Is it disjunctive? Does it start with a disjunction? What does it start with?
It's if, right? If then, so it's not.
It's not categorical.
So it's just, no, the
Hypothetical.
Hypothetical! It starts with a conditional statement.
Yeah.
Don't you remember? This is a conditional statement. If P, then Q. Right? That's what horseshoe stands for.
Mm-hmm.
And that's a conditional statement. So it starts with conditions, a hypothetical syllogism. Then it actually affirms your antecedent. Right? This is your antecedent, this is your consequent. Quickly, we forget everything. Well, that's why it's good to have a review. Antecedent is here, consequent is here. You're repeating your antecedent, you affirm in it. And then that means your consequent follows with strict necessity. Why? Because remember, that actually is your sufficient condition. We can actually prove it now too. We can prove it. Let's prove it. So let's see. We have if P, then Q, then we have P, and the conclusion is Q. Remember how we do it in a shortcut? Let's imagine this whole thing is true, this is true, and the conclusion is false. Let's see if we're going to see a contradiction here or not. So, since we have very few operators here, we already know that our Q is supposed to be false, and our P is supposed to be true, right? We already have it right underneath them. So the only thing we really need to do is plug them here and see if we get a contradiction. Let's do it. So if this is true and this is false, are we going to have true?
No.
No. There you go, a contradiction. And remember, the contradiction is a good thing. It tells us that since this can never happen, the argument is valid. So we can prove it valid. This is a valid form, and remember, if the form is valid, any argument which has this form will also be valid. So this is a well-known valid argument form, modus ponens, MP. This is an argument which has this form. If 12 million children die yearly from starvation, then something is wrong with food distribution. 12 million children die yearly from starvation. Therefore, something is wrong with food distribution. You see, 12 million children die yearly from starvation is P. Something is wrong with food distribution is Q. We are repeating our antecedent, and that leads to our consequence. Same exactly form. Here they are using T and S because this is specific prepositions. 12 million children die yearly from starvation is T. Something is wrong with distribution is S. But lowercase p and q just can stand for that or for anything else for that matter. Next one is modus tollens. So if modus ponens repeats our antecedent, it affirms our antecedent, modus tollens actually does the to keep this here. Does the other valid operation, and that would be, even though we still start with if P then Q, say not Q. And remember that Q is our consequent, right? And our consequent is what kind of condition? So antecedent is necessary condition for the consequent. Consequent is, where antecedent is sufficient condition, and the consequent is necessary. So if necessary condition is not satisfied, then of course we can say that it cannot be P. Because P only leads to Q and Q are necessary condition. So that's this form. We're not going to do a proof on it, but trust me and you can do it yourself. It is also valid argument. It can never have false conclusion assuming these premises are false. They're true. Here's an example of argument which has this form. If Japan cares about endangered species, then it has stopped killing whales. Japan has not stopped killing whales, right? Not has. Therefore, Japan does not care about endangered species. Okay. Then there's pure hypothetical syllogism. We already saw this form. I did it and specifically told you guys that this is the only valid form when you have three conditional statements, and indeed it is the only one. So if P then Q, if Q then R, can validly lead to if P then R. It also is type of hypothetical syllogism, but we call it pure because it has three conditional statements. You see there's like a little chain being built here. If P then Q, if Q then R. And that by itself means that since this is sufficient condition for this is sufficient condition for this, then of course our first antecedent is also a sufficient condition for our second consequent. Here's an argument which has this form. If world population continues to grow, then cities will become hopelessly overcrowded. If cities become hopelessly overcrowded, then pollution will become intolerable. Therefore, if world population continues to grow, our first antecedent, then pollution will become intolerable, our second consequent. We're just kind of skipping this middle chain, the C in this case, and go straight from W to P. That's the valid form for pure hypothetical. And then the disjunctive syllogism. Remember the disjunctive syllogism, probably the most straightforward, starts with a disjunction P or Q, and then we eliminating one of the options, and the other option is the only one left. So P or Q, not P, therefore Q. We don't need to write it the other way around. So we could do this if P or Q, not Q, therefore P. But we don't have to. Why not? Because P and Q stand for anything, and P or Q is equivalent to Q or P, and in that case, not P is equivalent to not Q already. You don't need to spell all of this out, right? Because it's not specific letters anyway. It is pretty much anything. Okay. Let's see the argument which has this form. Either Harvard or Princeton is in New Jersey. Harvard is not in New Jersey. Therefore, Princeton is in New Jersey. So we saw this before. This is yet another valid form. Now, substitution instance of modus ponens. Remember that modus ponens, this first one, if P then Q, P therefore Q, And that's a meta language. It can stand for anything. So let's say we have this argument. If not A, then B, not A, therefore B. Can you see that this is actually the same form? So you have to understand why it's the same form. We have a negation here, we have a negation here. So do we change the true value? We do. So let's say A is true. What would be not A?
False.
How about another not A?
True.
Why?
Still false.
Still false. We're not changing anything. If not A is false, not A is also false. It's still the same letter. And still with negation. So if we call it P and say our P is false, it will still be P. So that's why if you don't change the true value, you don't need to add negation here. Right? That can be described. Remember, it's like a little matryoshka. That P can stand for anything. It can stand for A. It can stand for A. It can stand for not A. It can even stand for like not A, therefore B. The whole thing can be just P. This structure will be preserved as long as you do not change in the true values and your overall kind of structure is the same. And if you look at it, it is the same. We have some sort of antecedent here, we have consequent here, we're repeating our antecedent here, and we lead into our consequent. So it is still, if P then Q, P therefore Q. When not A and B are mentally substituted, respectively in place of P and Q, of the modus ponens rule, then you should be able to see that the argument on the left is an instance of the rule. Okay. Now let's look at this one. It looks like there's a lot more stuff, but note that it again has the same structure. Here we have A and B, and here we have A and B to the left of our horseshoe, so this is our antecedent. We can replace it with P as well, right? Here we have C or D, and here we have C or D. So if this is our consequent is repeated here. So you see it's again the same structure. As long as we preserve it, like if it was C or D and here we suddenly would come up with like C or F, now that would be different. But as long as it is the same as here, that is the same structure and it is still a valid argument. You can just mentally substitute A and B for P and C or D for Q, and as long as you are consistent and you see that you are preserving this structure, there's really nothing new. Now another thing is order of the premises. Order of the premises doesn't matter. We can switch them around. Why? Because remember that in the end of the day, all we care about is that if all our premises are true, the conclusion cannot be false. In which order that happens doesn't matter. In language, we may place them in certain order for a variety of reasons in English language. But in propositional logic, it doesn't matter which order the premises are in. You can switch them around if you want to. So that would also be the instance of the same form. Now if you copy it exactly the way it is, if you call A P and then if B then C Q, you can first write it this way, but you can immediately see that you can flip this premises around and then you will have perfectly valid form. So that would also be a valid argument. This is other 3 examples of modus ponens. If you think about them for a few minutes, you will see why. Let's start on the left here. If not F is P, well, this is also not F, so it also is P, right? And if G triple bar H is Q, well, that then is Q. So that's exactly the same form. Same thing here. A or B. Well, if that is our P, we are repeating it here, so our second line is also P. If not C or D is our consequent, we're repeating it here. So if this is q, this is also q. And finally here we have the order of the premises reversed, but if you think about it, this is the first premise, this whole thing would then be our, this thing would be our antecedent, and this whole thing would be our consequent, right? So this is P and this is P, and this is Q and this is Q. Except P here first, Q, if P then Q second, and we can flip them around, and it would still be modus ponens. So how can you construct a proof? If you're given an argument, let's look at it step by step. The first step is obviously to symbolize it. Symbolize the argument. Let's see. So if asterisk switch leads, that would be A, right? If asterisk switch leads, then the Braves will not win further. Since they will not win, so now if Cubs retain their manager, C, then the Braves will win, B. The Astros will switch leagues, therefore the clubs will not retain their manager. Yeah. Okay. Now, in order to continue with the proof, it makes more sense to write the not C to the right like this, instead of writing it here. As you can see, that's pretty much the same thing, but why? Because like now we're actually going to try to continue, and the conclusion shouldn't get in the way. We have three premises, we have the conclusion, right? This is our argument in symbolized form. What happens next? Always begin by trying to find the conclusion in the premises. If it's in the premises, like here for example, we do have C. We don't have not C, but we have C. Always look for the main operator of the conclusion for the clue about how to derive it. So this is the first step. You symbolize your argument, you put the conclusion to the right. Look at premises 1 and 3. Do they seem to lead to some conclusion by themselves? Using the rules we just described, which hopefully you guys paid attention about the rules. So let me write it on the side so you can see it a little bit more clearly. This is 1, 2, and 3. Right? Using 1 and 3. So 1 is if A, then not B. And 3 is A. If we replace it with P and Q, what do we have? Yeah, we have if P, then Q, P. So what does it lead us to?
Q.
Q, which in this case is what?
Not C.
Not B.
Not B. Okay, so that is actually modus ponens, it's MP. So the way to write it on the right side, you put which premises you are using, right? 1 and 3, 1 and 3. You are using the rule MP, and you are getting not B. And this is your fourth line. So this is what you derive from these two. The number 2, line number 2, for now you're not really touching it. Right? So this is the second step. The third step, we can also do the same thing with 2 and 4 and using modus tollens. Let me do it on the side for you as well so you could see clearly why. Now which rule to use, that's where you have to be creative, right? Because you're trying to get to your conclusion. What you're trying to do here is to prove your conclusion, not see. But how you get to it depends on what you are given, so it's not mechanical process. Okay, they already lead you through it here. They give you the, okay, so 2 and 4 and modus tollens. What are the 2 and 4? So 2 is if C then B, right? That's your 2. Your 4 is not B. And remember modus tollens, so what does it say? If P then Q, not Q, therefore not P. So what are we going to have here then? Not C. Oh, hey, look, that's what we needed. We needed to get to our conclusion, which is not C. So now we have proven it. You see, you actually showed step by step, but your conclusion does in fact follow here. So we just add this fifth line. We are saying which rules we are using. So here 2, 4, and then T. And we are getting to not C, which is what we needed to prove in the first place. This is our conclusion. We have reached it. So in each case, we are trying to prove the conclusion by showing step by step how applying these rules we can get there. Which rules? Like I said, that's a little bit of an art. Sometimes it's hard to see. Sometimes even for me it may be hard to see. It may take a few minutes to think about it. In some situations it's easier. First examples will be easier on a homework and what we do in class. Then it may get more and more complicated. In some cases it's a one-step process. You can just find a rule there, boom, you got your conclusion. In some cases 2, 3, 4 steps. In some cases you may need 15 steps. I don't think we have anything as complicated as that, but in real life it may be the case. So you try one way, you get dead end. You try the other way, you get dead end. And then you finally find it. That's the idea. But in essence it is rather simple. You have to understand the rules. These 4 rules which we started the class with, and we will add another 4 on Thursday. And you have to apply these rules. Obviously, all the examples do have correct answers there, so if you can't find it, there's something going wrong. In real life, it may not have an answer. So this is also, again, related to what computer programming is, right? Nobody is going to tell you what to do. You have to find your own way. You have to discover the way to get to result, which you know what you actually are looking for. The result is something you already have an idea about, but how to get there, that's the question. So this is also all examples of modus tollens, right? If you think about it, remember this is our modus tollens. P then Q, not Q, therefore not P. So if this is P then Q, not Q, not K in this case, therefore not P. If this is our P and this is our Q, again, know that it's already negated, but we can negate it twice. Negate, negate. And it's the same thing as not negating at all, right? But actually, here it's best to add another negation just so it would be clear, so you wouldn't get confused. But the idea is if you negate something twice, it's the same thing as if you never negated it in the first place. It's like flipping the coin twice, you get to the same result. And similarly here, again, it should be negated, so you negate it twice, which is the same thing as not negated it. Same modus tollens structure, and here they change in the order of premises, but it doesn't matter. If you flip the premises, you'll see it's modus tollens. And there's not like a lot of premises, it's just 2 premises, so you can always flip them just in case and see whether it is modus tollens or not. Okay, if the conclusion, let's look at another example. Let's say you have something like this. Conclusion contains a letter that appears in a consequent of the conditional statement. So whatever the strategies are, you will have to kind of think about them on your own. We're going to go through them now in class, but in order to really learn it, you need to do a lot of practice. The more practice you do, the more you will learn this stuff. So you are given something like this, right? That last line shouldn't be here yet, but it's already here. If A then B, then C or A, and the conclusion is B. So here you can use 1 and 3 as a modus ponens. If A then B, A, therefore B. That's the easiest one. If you can find the one rule to get one step to your conclusion, that's of course ideal situation. Okay, another example of strategy you may employ is, in this case, using modus tollens. If the conclusion contains a negated letter and that letter appears on the antecedent of a conditional statement in the premises, consider obtaining the negated letter by modus tollens, right? So, if C then B, if A then B, not B, and your conclusion is not A, you can see that if conclusion is not A and you have A and B and you have not B, modus tollens kind of here very clearly begging to be used. Again, this is just one line solution, very simple. You're using 2 and 3, you don't need 1 at all. Don't worry about the fact that you don't need it, but you can show here that if you are using 2 and 3 in modus tollens, you will get not A just based on that. Pure hypothetical. Let's look a little bit closer on this. So you see that your premises in this case are if B then C, if C then A, and if A then B, and your conclusion is if A then C. Now, one thing to remember with pure hypothetical syllogism is that you can have different order of premises and it's not immediately clear. Remember, the pure hypothetical is if P then Q, if Q then R, and the conclusion is if P then R. But you can also have if Q then R, if P then Q, we're just reversing the order of the premises, and the conclusion is still if P then R. So that's one thing to remember. Sometimes you may not immediately see how, in this case, pure hypothetical works. But if this is your first premise, and this is your second premise, you see it is if A then B, and if B then C, right? Can you see that? And so that's how we get from that to our conclusion, if A then C. So you may try to switch the order of the premises kind of in your mind or on the side if you have trouble doing it in your mind. And then you will see that using 1 and 3, it is pure hypothetical syllogism, HS. And that's how we are solving this. So remember, HS stands for pure hypothetical syllogism, 3 conditional statements. If you only have 1 conditional statement, it is, even though it is hypothetical syllogism, but we either going to be using modus ponens or modus tollens. Yeah. Yeah.
Could you also, for the last slide, could you also do if B then A, or just,
What do you mean? If P then A?
if B then A for the conclusion?
Yeah, but this is your conclusion. You're already given the conclusion. This is kind of like extra line which initially shouldn't be even here. The way you would be given it on the homework, for example, is without this last line. It's already on the slide, but imagine it wasn't there. This is what you would have. And then you need to get to this conclusion using these premises. And I think the only way, using at least the rules we know so far, is to use 1 and 3 in pure hypothetical syllogism. So this is already solved. Now, with disjunctive syllogism, suppose you're given something like this. So let me just again do it on here so you can see. You would not be given the last line, right? You would be given something like this. If A then B, then second premise is A or C, third premise is not A, and the conclusion is C. And you need to prove it. So when you start looking at it, you can see I have my C here. It's part of this disjunction. And I also have the left side already negated on the third premise. So clearly remember that disjunctive syllogism, P or Q, not P, therefore Q, that's what we have over here, right? P or Q, not P, and therefore Q. So we got to it using premises 2 and 3, and it is disjunctive syllogism. So that's already there, but like I said, just imagine it's not there. Sometimes there's more than one way to get to it, but that can get confusing, so for these simple exercises, they're not letting you see these kinds of options. Okay, so here's an example without a solution yet. Let's look at it, let's think about it together. So this is what we have. Suppose we are given it, let's say on a homework or wherever. The first premise is if A then B. The second premise is not A, therefore C or D. We're getting a little more complicated, right? Third premise is not B. Fourth premise is not C. And we need to get to D. How can you get to D? Can you prove it? So where is your D? You have D somewhere there, right? So where you need to get to? You need to get to this premise. But you can't get to it directly. So one way you can think about it is try to see what else can you figure out here. Do you see any kind of rules applicable to this situation already? Which premises and which rule would you use? Huh? 1 and 3, right? 1 and 3, and if you do 1 and 3, which
empty.
empty. 1 and 3, empty, and what is it going to give you then? Nothing. Okay, that's already good because we have not A here, right? So we can use that as well to get to what? Not D yet. We can get straight to D. Well, eventually we'll get to D, but at this step, for line 6, because that's a little more complicated, right? If we use lines 2 and 5, and which rule? Modus ponens. 2 and 5 and modus ponens, what are we going to get?
C or D.
C or D. So that's already helping us here, right? But we need to get to D, so what do we need?
4 and 6.
4 and 6, because we have not C, right? And disjunctive syllogism. So now, if we put not C underneath this, which is kind of did, we will get what?
D.
D. And that's what we need. So you see, we build a longer chain, and we got exactly where we needed in the end. That's the idea. Now our proof is completed, because we finally got our D. It's not always easy in one step. Like I said, the first exercise is one step, but you may need 2 steps, 3 steps, 5 steps, who knows how many steps. We've only learned 4 rules, we'll add 4 more next time. So it does get more and more complicated, but that's the idea pretty much for the end of the class. Because what we're going to do in chapter 8, we're just going to use these rules and some additional rules for predicate logic. Predicate logic is more complicated than propositional, but the idea is still the same. In predicate logic, you cannot use truth tables. Truth tables are fantastic, but only if you have these simple operations. However, predicate logic adds so much more in terms of operations that you're no longer capable of calculating every single truth and falsity as we did in chapter 6. If you could, it would be fantastic, you would get the result, but you can't. And if you can't, you have to use these type of rules to show that your argument preserves the validity. And you can, but it just gets more and more and more complicated. Okay, so this is also all examples of pure hypothetical syllogisms. Again, if you think about it, you see they all have 3 horseshoes. And if you imagine that this is your P, this is your Q, and this is your R, then you will see that all of them have this form. If you think about it for a few minutes, It's all in the book too. They all pure hypothetical syllogisms. Okay, here's another example. Let's again try to do it together, step by step. So we are given first line is if f and g, second line f or h, third line not g, fourth line if h and g, therefore I. And you need to get to if f then I. Okay. Now you really don't have if f and I here at all. So you need to be more creative. But at this point again, you can just do your best. Just look at this part and try to see, can we get anywhere from here with the rules we already have? What can we use?
I think we could use line 1 and 3 and
Yeah.
use MT.
1 and 3 and empty, and we get what? Not F. Okay, that gave us something. Now can we use something else now? This is not F.
Lines 2 and 5.
Lines 2 and 5, exactly. And what we're going to get here, which rule?
Yes.
This
Disjunctive syllogism, and we're going to get in this line
H.
H. Because you see we have either F or H, not F, therefore will be H. Great. Now do we have anything else? Which lines?
4 and 6.
4 and 6, right? And which rule can we use for 4 and 6?
MP.
Yeah.
MP, modus ponens. And what is it going to give us? If G then I, right?
Mhm.
So yeah, that's going to give us this whole thing. Okay, but we don't need to have G then I, we need to go with F then I.
Mhm.
But which two lines can get us there? Yeah,
1 and 7.
1 and 7. And which rule?
HS.
HS, pure hypothetical syllogism, because here we have if F then G, here we have if G then I, and so we will have if F then I. There we go. So now we got there. Finally, we have proven the whole chain. Okay, hopefully you guys understand. It's just application of these rules, and in this point it's not very complicated because there's not that many rules, and you can see that in each case you can only apply one rule, so it's not confusing. You apply them and then you eventually get to where you need to go. This is also examples of disjunctive syllogisms. You can look in all these different ways, but the idea is the same. You have U here, which is P. You have something here, which is Q, not U, and therefore there's something, so that's again disjunctive syllogism. Here the order of premises is reversed, but if you put this premise up and this one down, you will see that this is your P, this is your Q, this is your not P, and this is your Q. So all of them are examples of disjunctive syllogism. Now, more complex example. Same idea. So we can again try to do it on the board together. Let's see. Sometimes it may get much longer. Sometimes, like I said, you may even get stuck and rethink it. So here we have the first premise. Okay. Let's see. So what can we apply here? What do we have? Which lines, which rule would you apply? But the thing here with them, there's only one rule really you can apply in this case. which
1
is
and 2 disjunctive syllogism.
Yeah, 1 and 2 disjunctive syllogism, and that will give you what? the right side here
Yeah,
in
the
brackets,
reduce
right?
the whole right
But
side.
you no longer need the brackets, because once you get this thing by itself, you can write it without the brackets. It still is kind of big, but at least there's no more brackets here. The reason you need brackets there is because you have this conjunction. Okay, now what can we do with this? We have an element of it there, right? So if we use lines, which ones?
3 and 5.
3 and 5, and which rule?
MP.
MP, we will get what?
C and
Yeah,
C
C,
and D.
C if
If
C
C
then
then
D.
It's C then D. Yeah, that actually is what we were, no, that's not here. This is G here. Okay, so we're not done. Let's see if we can get to C then G from this. What else can we use?
4 and 6.
Yeah, 4 and 6.
Okay, and that gives us what?
That's like a pure hypothetical.
Yeah, but like what, well, so 4 and
C,
6 and
yeah, if C then G.
your hypothetical is C then G. Okay, now we are done. That is what we need. Right? So once you got the word you needed, that's when you can stop. So they may look more complicated because of the large number of elements, but you have to just see this structure within these elements. Kind of like look at the main operators, because main operator is the most important one, right? That's why this is disjunction. That's why we learned main operators. You don't have to worry now about this horseshoe or this negation, but since you have this main operator here, you can figure out what part of this negation you may find within your argument, and then figure out from there. And remember, again, we didn't have to have this line to use it with negation as our first operation. For example, we didn't need it here. We didn't need it. But in some other case, you may have this line on your second line, or somewhere. It doesn't have to be second line, right? Then you can get to this. If this is negated, well, it would not be exactly like this, but you would have negation in addition to outside the bracket, right? One of the lines could go like this. Right? So this is what another line, based on the adjunctive syllogism, you could also get from this, because if P or Q not P, therefore Q is, like I said, exactly the same thing as if P and Q not Q, therefore P. That's the same idea. You're eliminating one of them, so you have the other one. It's just which one you eliminate. So you could get this part or this part depending on, here you have this eliminated, but if you have this eliminated, you get the left side. Now, in terms of invalid proofs, well, this is an example of invalid proof. Why is it invalid? If you think about what they are doing here, they're using 1 and 2 modus ponens, but what's going wrong? This is not C, right? So this is just some examples the book gives you to explain what you should not do. You cannot use just C. If your Q in this case is B then C, you can only use if B then C. There are several other examples of invalid proofs. So this is, they're trying to use pure hypothetical syllogism 1 and 2. Line 2 must negate A not asserted. In this case, again, this is invalid. Use of MP, because this is your consequent, not your antecedent. There's several other ones. Well, actually, I'm not going to go through them because we don't have that much time left. But you can take a look in the book. This just basically explains to you what not to do. Just common mistakes kind of thing, right?